All right, so rather than talk about the symmetries in any more detail than that, what I wanted to do is actually do something a little different with this theory. So there's lots of things we could discuss here. But the thing I want to discuss is actually treating a bound state in a field theory. This field theory has a very nice property that we can calculate everything. So we can actually see how you're supposed to treat bound states exactly, because we can actually just look for the pole that corresponds to that bound state in this theory. That's what we're going to do. So usually if you have a bound state, it's either something that's non-perturbative that you have trouble dealing with analytically, like in QCD, or Coulombic. Even then, the calculations get kind of hairy, although you can deal with it there. But here, the calculations are very simple, so we can really follow all the steps of properly dealing with a bound state. And the bound state has something to do with nature. It's a state in nature called the deuteron. So the deuteron is a bound state of a neutron and a proton. It has isospin 0, spin 1. So it's in this 3s1 state that we talked about. And when you want to look for a bound state in field theory, what you do, if you may have heard of this from the lattice point of view, what you do is you write down some interpolating field that has overlap with that state. So what would that be for us? That would be this operator that we called pi 3s1, which had the quantum numbers for I equals 0 and s equals 1. And we can build an interpolating field out of our n transpose n. And actually, any interpolating field that we write down here is equally good. Lattice QCD people like to tune what they write down in order to improve the overlap with the state. But for our purposes, the simplest possible thing will be enough. And then you can ask the question, is the deuteron in the theory? And to answer that question, you can just look for the pole that would correspond to that state. And the advantage of this theory is that we can just look for that pole analytically. So let's do that. So I'll write down a Green's function for the two-particle state. Which is just the time order product of two of these interpolating fields. And then ask the question, if I look at that time order product, is there a pole that would correspond to this state? I.e., somewhere, is there a pole which would behave as follows? Some kind of z factor, and then in this case, because of the way we've scaled energies, we would just be looking for a pole that's linear in the energy at some negative energy corresponding to the binding energy of that state. So remember that we pulled out the mass of the nucleon. That wasn't in our Lagrangian. So really, if you think about what the sort of energy of this state is, it's two nucleons. So it's got the energy of those two nucleons. But then there's a little bit less, because it's a bound state. And this is the amount by how much less. And so the energy for the pole is negative. E bar is less than 0 because it's how much less than the two nucleon mass. So this E bar is the two nucleon center of mass energy. Which, in the conventions we were using last time, is we had energy E over 2 for each of the nucleons, so the sum would be E. There's some kinetic term as well. So what are the diagrams that we would consider to do this? Well, at lowest order, it's just our friends, the bubble sum. And in fact, when you go to higher orders, we also had bubbles there. So to answer this question, we insert the field, we create two nucleons, and then they can interact with C zeros, and then we annihilate them with our interpolating field. So these are just our C0 bubbles. Okay, and those are very easy to compute. It's just a geometric series that we already computed. And instead of having two nucleons in and two nucleons out, we just have this deuteron state in and deuteron state out. Okay, so the Green's function starts with one of these and then just iterates into a geometric series where sigma I could define as two particle irreducible C0 graphs, so sort of taking out the C0 iterations. So the sigma 1 that I'm talking about here is just this bubble all by itself. And that's something that we computed before. And in these renormalization schemes that we like, it just comes out to be this. So there's an M out front, M nucleon. That's an M, not a mu. And then in terms of this E bar, it just comes out to be that. So you could think of making a positive energy by taking E bar to be minus E bound, which is less than 0. And then the square root would be square root of M EB. And it's convenient to define that to be something. So I'll call it gamma B. So that's some quantity greater than 0. And with this little notation, this square root of minus M E bar minus I0 is equal to minus IP. And we're looking for whether that would be sort of going over to this gamma B. Sorry, so this is equal to gamma B. So gamma B is just like a momentum version of the bound state energy, absorbing the extra I. Okay, this is what it would have been previously, but now it's gamma B. So we know what G was. We already computed it earlier. G was just proportional to 1 over A plus IP. And now if I just make that replacement, which is why I wanted to derive that, because I wanted to just see how I would replace the IP, becomes 1 over A minus gamma B. So gamma B is a kinematic variable. It's like a momentum, but it's the right kinematic variable to be talking about for the bound state. It's a positive thing. And you can see there's a pole. Okay, so there's the pole corresponding to the Detueron state. It just corresponds to gamma equals 1 over A of the 3s1, which in nature is like 36 MeV. It's greater than 0. If you looked at the other channel, the 1s0 channel, then the scattering length was negative. So then both terms would be negative, and there's no pole. Okay, so for the 3s1 channel, we have a pole. That's the physical Detueron state. For the other channel, there is no pole. And the binding energy that you would get from this is gamma B squared over M with our conventions, which, if you calculate it, is 1.4 MeV. And that's not ridiculously different than the real binding energy of the Detueron, which is 2.2 MeV. Okay, it's the right order of magnitude. All right, so that's the Detueron. It exists in this theory, and we could perturbatively correct towards this correct binding energy. Okay, so this Detueron really exists in the field theory, and that means we can calculate properties of the Detueron with this field theory. We can calculate scattering processes that involve this bound state, and it's no more difficult than doing calculations that we would normally do with free fields. And we just have to, if we want to do something with the deuteron, we have to go to the right pole. That's basically what it boils down to. So in order to show you really how to do that, I'm going to give one example, calculating something non-trivial that involves a deuteron. So we'll calculate a form factor for the deuteron. So this is a nice example, if you like, of really showing you how to use the LSZ formula, which you learned about in a very sort of abstract way at some point, how to use it for bound states. Because here we have a bound state exists in the theory, and if we want to derive properties of that bound state, we better properly use the LSZ formula for that bound state. So let's see how that works. OK, so what we'd like to do is we have some deuteron state, and we'd like to take the matrix element with the electromagnetic current. And if you work out what possible form factors you can have for this matrix element, there's actually 3. And I'm not going to spend much time talking about the sort of different couplings with spin and stuff that correspond to these different cases, but I'll list them for you at least. Provide you some additional references if you want to dig deeper into this. So there's a magnetic, electric, and quadrupole form factor. The charge of the deuteron tells us that this electric form factor should, at q squared equals 0, should be 1. The magnetic form factor is like the magnetic form factor for an electron, in the sense that if you go to q squared equals 0, then that's giving you the magnetic moment. But here it's the magnetic moment of the deuteron, not the magnetic moment of the electron. So it's a non-trivial number in this case, whereas here it's just 1 because charge is conserved. And if we wanted to think about putting electromagnetism into the nucleon theory, which we haven't so far, then we would turn our derivatives into covariant derivatives. So d mu nucleon, we have to write down a charge matrix that couples, that takes into account that the proton has charge but the neutron doesn't. So this is that charge matrix for electromagnetism. OK, so it's not difficult. So that's easy enough. Just change your derivatives into covariant derivatives for both d0 and d partial and d vector. There's also some additional operators that you have to write down. So there's operators, for example, that are just contact interactions with the electric and magnetic fields in principle. And the first such one that shows up, just by way of sort of telling you the range of possibilities, would be something like this, where you just have a sigma dot b magnetic field insertion. So this is the magnetic field for electromagnetism. And so if you want to think about the type of Feynman diagram you'd draw for this, you'd have 4 nucleons, and then you just have a photon coming out, right? And if you want to think about where that could possibly come from, there's one really easy thing to think about, would just be to have a pion exchange, and maybe it's a pi minus, and the photon couples to a pi minus because it's got electric charge. And when I integrate out the pion, then I just get something that looks like this. Could be any exchange. It could be a rho minus. Or anything will give an operator that looks like that. OK, so there's additional contact interactions involving electromagnetism, and you gauge the derivatives. Then you can put electromagnetism into the theory. Gets a little more non-trivial then. And that's what we need to do if we want to talk about electromagnetism coupling for the deuteron. But I'm mostly interested here in how the LSZ works. So what does LSZ say? So LSZ says that if I have this state, P prime, J out, J mu electromagnetism, P I in. I is like a spin index because we have a triplet under spin. Then this is how you should calculate it. So Q is like the, well, I guess I'm in momentum space all of a sudden. Well, no, Q is just the P minus P prime. E and E bar are related to the P and the P prime also. And what I do is I have some Z factor out front, which is the bound state Z factor. LSZ tells me to be careful about that Z factor. These guys here are just 2-point functions, and that's because I have to truncate the lines. This is truncation by 2-point functions, but they're 2-point functions for the bound state, so 2 lines. And then this is the 3-point functions. Okay, so for the 3-point functions, what would the time order product be for that? It's a time order product of 3 things. So the 2-point function we already defined, it was just a time order product of the 2 deuteron fields. And the 3-point function has an additional electromagnetic current. Which we would formulate, all the couplings here this way that I was talking about over there. So in terms of diagrams, which are easier to think about in some ways than time order products, we have the 2-point function, which if I just define all possible 2-point functions as G, then this is the thing that was our irreducible C0 contributions plus iterations of C0s, right? Since the C0 is a non-perturbative coupling, we have to iterate. And this is what we already said you could define as summing up that geometric series and then just define it as something which is the full Green's function in terms of this irreducible piece in the usual sort of way. And then for this other G, I'll draw a blob, which I'll also call G, but with an additional photon hanging out. Those are all 3-point functions. And in a kind of a similar notation, I can have kind of an irreducible piece, and then I can have iterations with C0s. Etc. And if I sum up those irreducible diagrams, I can write the full Green's function in terms of the irreducible pieces, again in a similar sort of notation. It's just gamma, which carries the indices. And then there's just a couple of, now there's geometric series on both sides. So when I sum them up, I get that. OK, so this is giving you the ingredients that we need to plug into this formula. We need G inverse. This is G. The 2-point. We need the G mu ij, which we can write in terms of the irreducible guy like that. And then the last thing we need is this bound state Z factor. Yeah?
But the full factor has a contribution that you just erase?
Yeah, I'm kind of using a shorthand here with this T product for all the diagrams that come from what I was talking about over there. Yeah, I kind of wrote it as an electromagnetic current, but really what I mean by it is sort of all the ways that electromagnetism can appear in the effective theory. So you can think of formulating a current in the effective theory by just sort of looking for one photon, lopping it off, and then writing down that operator, all the operators, and that's really what I mean by this, J mu. Any other questions? Okay, so what's the final thing we need, which is the bound state Z factor. So that's, when we look back at this kind of form that we had for G, we said it's IZ, but now let's denote the fact that Z is really in principle a function of E bar, and it's really the residue of the pole. And what Z is, Z that appears in the formula over there, it's Z at the pole. So that's where I set E bar equal to minus BD in the numerator. So this is the residue of the pole. And with a little bit of manipulation, we can write that as the following. We can relate it to a derivative at the pole. Okay, so take the inverse, take a derivative to sort of get just this factor, take an inverse again, you can extract off that residue, killing off some other pieces by going to the pole. Okay, so I won't go through the derivation of that little manipulation, but it's a straightforward consequence. And if you put in kind of the formula that we had over here for G, and you do that, then you can write a formula in terms of sigma. And after that kind of manipulation, it's again just some algebra to show that this is true. So now we can put all the pieces together. We have this formula. We have this formula. We have this formula. Put them into the formula up there, and what we find is that we can write the kind of result of it using LSE in a kind of very compact way, and just in terms of irreducible things, C0 irreducible things. And it's not just the irreducible 3-point functions. There is a contribution from the 2-point function, which is, in this case, d sigma dE bar, where you take E bar and E bar prime, incoming and outgoing energies, to be the right energies for the bound state, which is minus the binding energy. Okay, so this factor came from here. There was a sigma squared in the numerator. But when I take the inverse of two of these guys, there's a sigma squared in the denominator, and those canceled. The inverse of these guys also had factors of 1 plus IC0 sigma in the numerator, and that canceled these factors here. So the only thing left is the gamma and the d sigma dE bar. Okay, so that's what LSC says in this situation. And it's actually important to take this factor into account. If you didn't take this factor into account, you wouldn't even preserve, for example, that the charge of the deuteron is 1. I mean, it's quite important. If you look at this at lowest order, and you just look at the electromagnetic current for the electric case, and you can do that with J0, looking at the D0, and we can use our previous calculations to figure out what the 2-point function is. when I go to the pole, it's just this factor where gamma B would be set equal to exactly the binding energy. Okay, so that's just from the trivial diagram. And then the first contribution that comes into the 3-point function can be calculated. It's pretty straightforward. It gives a tan inverse, actually. And that just comes from coupling to the electromagnetic proton that's inside the deuteron. So this is the proton, which has an electromagnetic coupling. This is the neutron. Okay, and that gives this formula. Take the ratio, you get the lowest order form factor. This is a systematically improvable thing, so you can do NLO, you can do NLO, etc. Okay, so we can really calculate properties of the deuteron and check whether they work experimentally, and this works extremely well experimentally. You actually don't see the violation of charge conjugation, conservation in the form factor until you do NLO. Then you really see that you need this guy in order to make sure that the charge is conserved. There would be some pieces that would show up that would seem like they were correcting the charge, violating electromagnetism, magnetic gauge invariance until you, but then when you put the Z factor in, the Z factor contribution in, everything is nice. And this theory has actually been used to do phenomenology. So just to give you some examples of that. So you can do a process like neutron on proton produces a deuteron and a photon, which is something that shows up in Big Bang nucleosynthesis. And it's been calculated to N4 LO in this effective field theory. Okay, and it provides the most accurate way of determining the process for Big Bang nucleosynthesis. You could reverse it, talk about deuteron breakup. You could do processes with neutrinos on deuterons. So you could have neutrinos deuteron scattering to proton-proton E minus, which is the charge current process at SNO, or the neutral current process at SNO. All these things are within the realm of things that you can talk about in this effective field theory. Okay, so it has some uses.